Hey class, Mr. Moyden here with a video lesson regarding a better understanding about position, velocity, and acceleration. So we saw in class this hierarchy, so you don't have to write this down again because hopefully you got it in class last week, but essentially what it's showing you is the relationship among these three quantities. Position tells you where you are, velocity tells you how fast you're going and what direction, and acceleration tells you how fast the previous quantity, velocity, is changing. So to go from one quantity to another, you simply take the derivative, usually with respect to time. So d dt is a concise way of saying that, the derivative with respect to time. And you'll see that I have marked here the units that these things are measured in. Distance answers the question of position. Distance divided by time, or distance per time, is velocity. And distance per time, or distance per time squared, is acceleration. And various different representations. It's position, the first derivative of position, and the second derivative of position, respectively, which can be represented these ways, or you can call it velocity on its own, in which case velocity is, acceleration is velocity's first derivative, which you see here and here, or its own function called acceleration. So all that is review. Let's take a look at how we can actually understand these terms in a bit more context. And it helps to understand a couple vocabulary words / graphical representations or ideas related to motion as it relates to calculus. So the first thing that people often have trouble with is distinguishing between velocity and speed. Remember that velocity gives you two pieces of information. It gives you direction and speed. So that's why you can have negative velocity. It tells you that you're going either downwards or leftwards, right? So speed, by definition, is defined as the absolute value of velocity. So speed is the absolute value of velocity, which essentially removes the direction element and simply gives you, as expected, the speed. So that's pretty easy to get your head around, but just make sure when you see negative velocity, it's simply telling you direction. This next part is a little bit harder to wrap your head around in general, although the following graphical example we'll see hopefully will help you. And that's to figure out if an object is moving faster or slower at a given time. Because just because the speed is negative doesn't necessarily mean it's slowing down, could very well mean it's speeding up. So another way to ask this question, faster versus slower, is the speed increasing or is it decreasing at a given time? A quick and easy way to figure this out is if speed and, whoops, I already messed up. Let me fix that. If velocity and acceleration have the same sign, that means you're going faster. And if those things have different signs, that means you're going slower. Same signs faster, different signs slower. Now, it shouldn't be too hard to think about the case where they're both positive. If you have a velocity graph or a velocity function, and that velocity function is positive, but it's also increasingly positive, essentially your velocity is getting faster and faster and faster, and that's what we think of when we think of acceleration. But keep in mind the same thing could be true in the negative region. Remember, a negative velocity, these are both velocity graphs. A negative velocity is simply telling you you're going backwards. So in this particular instance, you'll notice that the velocity is negative because we're in the lower part of the graph, but it's also getting more and more and more negative. So the speed, or the absolute value, would flip it up if you think back to graphical transformations of functions. So we'll see some more of that in the following example, but try to think about the same sign being essentially you're moving at a higher and higher distance away from the, when I say distance, I mean on a graph, from the zero line here in either direction. A couple other terms that'll help to understand when you see the idea of at rest. All that means is your velocity at a given time, your v of t, is equal to 0. Remember, velocity is a measure of how fast something is going in what direction. And if you're not going at all, if you're at rest, then your velocity is 0. So that's essentially what that means. A couple more terms. when you see a change in direction, that means that velocity crosses the horizontal axis, which is normally time, although not always. So anytime you see on a velocity graph something like this, that would be a change in direction, right? It's going from upwards positive or right, either way, upwards to downwards negative velocity. On a position graph, it's pretty clear because the graph literally changes direction, right? So if this is position as opposed to time, then you have that kind of behavior there. Displacement is something people often struggle with. Displacement is essentially, let me use the correct variable there. X and S are often interchangeable. We use S oftentimes for position. My pencil keeps breaking, which is a bummer. Displacement is essentially the difference between your position at a given time minus your position at usually the initial value, but it could be just some other time. So essentially the net change in position. And we'll see more of that in class. I just wanted to expose you this idea of displacement being where you are now minus where you were before. That's your displaced value. Now keep in mind, that may not capture all the movement. For example, I started this day at home and I drove, but I also returned home, which means my position, my displacement is 0, even though I did travel, because I started and ended at the same place. So distance traveled versus displacement, they're not exactly interchangeable. And finally, we have velocity increasing or decreasing. Remember that velocity's rate of change, or the derivative of velocity, is better known as acceleration. So if you have an increasing velocity, that means your derivative or slope of velocity is going to be positive, and a decreasing velocity means your slope or rate of change or acceleration is going to be negative. So just some fairly basic ideas to think about when it comes to motion. And let's look at a graphical example for a couple of questions here. Let me get my pencil to work. Note to self, use a pen next time. Oh well. So here's a concrete example dealing with our old friend, Mr. Frumble. So suppose Mr. Frumble lives on a straight road. He leaves his home in his car and drives such that his velocity in kilometers per minute is graphed below, where t is minutes since departure. So this is going to be the t-axis, and this is going to be the v of t-axis. And the units here are important. This is going to be kilometers per minute, and this is going to be in minutes. So a couple questions here. First is, what is Mr. Frumble's velocity 2 minutes after departing? In other words, mathematically, what is v of 2? Well, notice this is a graph of velocity, right? So all you got to do is go to the t of 2, input, output is, in this case, also 2. So that means 2 kilometers per minute, which is about 75 miles an hour. Mr. Frumble likes to speed. Next question, is Mr. Frumble at rest from t equals 2 to t equals 3? So we're talking about this particular part right here, and his velocity graph is here. Is he resting then? Well, you might think, well, the graph is flat, so probably. Well, remember, at rest means, is the velocity equal to 0? Notice that the velocity values from 2 to 3 are in both, for this entire interval, the velocity is 2, right? So it starts at 2, it stays at 2. In other words, he's not accelerating. In fact, the slope being 0 here tells you that the slope of velocity or acceleration is 0. He's essentially coasting or on cruise control for this particular period. He's staying at this constant speed, right? So is he at rest? No. His velocity is simply remaining constant. Next question. When does Mr. Frumble change direction? What is his acceleration then? So changing direction, recall, means a sign change from positive to negative. So sign change in velocity. Sign change in velocity. Well, hopefully you notice that the change in direction is not going to be here or here, because in both instances, his velocity, the value of this graph, is positive, and it's still positive, but rather we're right around here. His velocity before 4 is positive, albeit just barely, and after 4 is negative, albeit just barely, but getting more and more and more negative. So when does he change direction? That would be at time t equals 4 minutes. What is his acceleration then? That means what is a of 4? Well, a of 4, another way to ask that is what is v prime of 4? What is the slope of the velocity graph at 4? Well, oftentimes if we had an actual function, we could probably take the derivative and figure that out. But since we don't have a function, all we have is a graph here. Remember that derivative is slope, so what's being asked for is the slope of this graph at 4. And if you look carefully, you see you have, for this linear segment here, a rise, or in this case a drop of -2, and a run of +1. So the slope or rate of change of the velocity graph would be -2 over 1. Now units are important here. Essentially, the vertical change unit is kilometers per minute, right? That's this unit. And the horizontal unit is minutes. And that's where you get the idea of kilometers per minute. And that's why acceleration has this unit per time squared. So kilometers per minute squared. -2. Next question here, is Mr. Frumble speeding up or slowing down at time t equals 3.5 and at 4.5? Well, 3.5 is right around here. Is he slowing down or is he speeding up? Well, notice that velocity of 3.5 appears to be 1, and acceleration at 3.5 is still the same line, but you'll notice even if we didn't know the number, it's a negative number because it's downhill. It's the slope. Remember, a of 3.5 is the same as v prime of 3.5. Both of those are going to be negative, and we know it's actually -2 from the previous problem, but let's just see that it's negative. Since these are different signs, at 3.5 he is slowing down. At 3.5. Well, at 4.5, let's take a look. That's right around here. His velocity at 4.5, remember that's just the velocity graph, so simply the output at 4.5 is -1. Just for units here, that's kilometers per minute. Forgot to do that for the last one. And the acceleration at 4.5 is the slope of the graph, which is just like before, same line, so -2 kilometers per minute squared. And since these are both negative quantities, we know that he is speeding up. Because if you think of this line as representing, right, in terms of, it's representing time, but in terms of its value vertically, right? Above means velocity in the positive direction, and below means velocity in the negative direction. He's simply going faster and faster and faster here, simply in the negative direction, or going backwards, back towards home, essentially. So that's why you can figure out that he's essentially speeding up at that point, right around here. The velocity is negative, but it's also decreasing, which is to say the velocity is getting more negative, so he's driving backwards faster. So that about wraps it up for this particular video. We've already gone a bit long here, longer than I intended to, but hopefully you can see some of these concepts coming into sharper focus. Alrighty, I'll see you in class.